Yes, hello Muzaffar, welcome on YourPedia platform and let's start your heat transfer snap for your final JKPSC interview.
Thank you, sir.
Muzaffar, what is thermal conductivity?
Sir, thermal conductivity, sir, it's a material property, sir, which tells us about the ability of a body to conduct, to allow the conduction of heat through it, sir.
So, okay. Can you tell me how the conductivity of solids changes with the increase in temperature?
Yes, sir. Sir, it depends upon sir, the type of solid, sir. If it is metal, sir, then there will be decrease in the thermal conductivity with the increase in temperature. This is because, sir, in solids, in metal, sir, we have free electrons and leads, sir. Because of increase in temperature, sir, there is increase in the leads vibration, because of which the free electrons collide more frequently. That's mean free part decreases and they don't pass in a particular direction. So because of the hindrance created due to lattice vibrations, sir, there is decrease in the thermal conductivity in metals. While, sir, if we talk about solids, sir, there by increasing temperature, sir, the lattice vibration increases. So as the main the main prime factor there for conduction is lattice vibration. So increasing lattice vibration increase the conductivity there, sir.
Okay. You heard about convection heat transfer?
Yes, sir.
You know, how it is different from conduction?
Yes, sir. Sir, actually, sir, here it is about the mechanism. Sir, in conduction, sir, this heat transfer takes place because of the presence of free electrons or lattice vibration. Sir, but in convection, sir, there is it is not actually, sir, independent mode of heat transfer. It is always preceded by conduction. Sir, in convective heat transfer, sir, the convection heat transfer takes place by the advection, that is the bulk motion of the fluid, and by diffusion, sir. For example, sir, if we consider some plate, a heated plate, where which the fluid is allowed to flow. Initially, what happens, sir, because of the no slip condition, sir, there will be the fluid there which is just adjacent to the solid surface, just sticks to it. That is the relative velocity between the two is zero. It attains the temperature of the solid surface, sir. So there's, sir, actually a boundary layer formation, sir. Inside the boundary layer, sir, due to viscous effects, sir, the velocity of the flow is less. So the heat transfer takes place mainly by conduction, and outside the boundary layer, sir, due to bulk motion of the fluid or advection, sir, the heat is convected away. So, sir, convection is actually the heat transfer by diffusion as well as by advection, sir.
Okay. What is Nusselt number? What is the significance of Nusselt number in heat transfer?
Yes, sir. Sir, Nusselt number, sir, it is the ratio of the convection heat transfer to the conduction heat transfer by the fluid. Sir, it tells us about the how dominating the convection heat transfer is over the conduction heat transfer by the fluid. Sir, for example, if, sir, Nusselt number is 2 and if the Nusselt number is 6, the fluid for which the Nusselt number is 6, this means that the convective heat transfer is dominating over the conduction heat transfer, sir.
Therefore, what are fins?
Sir, fins. Sir, fins are the extended surfaces, sir, which are provided in order to increase the effective surface area. So for the convection heat transfer, sir, and they are provided usually, sir, in order to increase the convective heat transfer, sir. For example, they are provided on engines, IC engines. In case of transformers, sir, we provide, or in different in industrial application, they are also provided. The main purpose is to increase the effective surface area so that the convective heat transfer is more, sir.
Okay. Wherefore, you know, like suppose we want to design the wall of a kind of cold storage plant. Okay.
Yes, sir.
So you are having a layer of 3 different materials.
Yes, sir.
So in which order you will keep them so that lesser will be the heat transfer? Suppose those 3, out of those 3 layers, 3 materials, all 3 layers are of same thickness. Okay, but their conductivity is different. One of the layer is having very low thermal conductivity, very, very low. Second one is intermediate, and the third one layer is having some, you know, some good thermal conductivity as compared to the other 2 materials. So in which order do you keep them?
Yes, sir. Sir, I think, but I'm not sure about this. I think, sir, the one having less thermal conductivity will be kept on the inner side so that the heat transfer is very less. And then, sir, the least amount of heat that gets transferred is then said, I'm not very sure on this. Let me think, sir. L over Ka. Sir, are they of same this length and area?
Yes, yes. All three are of same thickness.
Same thickness, T over A. Resistance is less in case of
area is also
this.
same because we are talking about wall.
Yes, sir. Sir, if we talk about in terms of thermal resistance, sir, thermal resistance will be least having for the one having more thermal conductivity. Sir, sir, I think it will
how
be.
You are calculating the total thermal resistance in that case?
Sir, initially I am calculating individually, sir. Sir, if they are kept in parallel, sir, then we will take the overall, sir, thermal resistance of these three.
So in wall, they will be in parallel or series?
Sir, they will be in. It is like this. Sir, in series.
In series. So what will be the total thermal resistance in series?
Sir, in series, sir, it will increase, sir.
No, it will be what? Like how you will calculate the total thermal resistance in case of different materials in series?
Yes, sir. Sir, it will be L. Total thermal resistance will be, sir, L over K1A plus L over K2A plus L3 over K3A.
So there will be any difference in the total thermal resistance, whether you are keeping any material at inside, in between the two materials, or outside? The total resistance is going to change, or it will remain same?
I think the total resistance will remain same.
It will remain same. So then how we can say that by keeping the lower thermal conductivity material inside, the heat transfer will be lesser, because the heat thermal resistance is not going to change whether you are keeping the insulator inside, outside, or in between the two materials. The total resistance will remain unaffected. Nahin?
Sir, there is something called, sir, thermal contact resistance, sir. Sir, that affects there, sir. For example, sir, if we keep them in contact, first having more thermal conductivity and second one having less thermal conductivity, sir, at the interface, sir, so there will be more temperature drop.
There, na? Contact resistance will be there.
Yes, sir.
So whether you're keeping inside, outside, or in between, the contact resistance will be there always.
Yes, sir, it will be there.
How we can remove? How we can minimize the contact resistance?
Yes, sir. Sir, by removing the roughness, sir, we can. Yes, sir. By polishing the surface, sir, we can increase the contact. Or, sir, we are doing something by providing some phase change materials, sir, having high thermal conductivity, sir, between at the interface, sir. Hello, sir. Yes, sir. For example, sir, graphene is provided. Graphene is provided to increase the interfacial resistance, sir, or some other this high thermal conductivity.
What is critical radius of insulation?
Sir, critical rates of insulation is that rates of insulation at which, sir, the heat transfer is more and the total resistance is less. Sir, it is an important parameter which helps us to find out whether the radius, how much radius we should reduce in order to decrease the rate of heat transfer or increase the rate of heat transfer. For example, sir, if we talk about this pipes carrying steam, there our main purpose is to provide much insulation. So, sir, the radius of insulation should be more than the critical radius of insulation, so that the heat transfer is reduced. While, sir, if we talk about transmission lines, the electric transmission lines, there, sir, it should be much lesser but close to the critical radius of insulation, so that the heat transfer rate is increased, sir.
Okay. What do you understand by steady state heat transfer, Mujaffer?
Sir, steady state heat transfer means, sir, when the properties that are not the function of temperature this time, sir. For example, temperature does not change with time, sir. It remains the same at different time intervals. Also, sir, this means, sir, when there is no accumulation of energy within the body, sir. Energy is coming in, heat is coming in and going out, sir.
What is Shea factor?
Sir, shape factor, it's also called configuration factor or wave factor, sir. It is used in radiation heat transfer, sir. It actually tells us about the net radiation heat exchange between the two surfaces, sir. For example, if one surface is say I and the second surface is J, if I just calculate Fij, that means that the energy fraction of the energy that is leaving the surface I and reaching the surface J. So actually, sir, in diffuse emitter, the radiation is emitted in every direction. So it is not possible for the surface B to every radiation won't reach the surface too. So we use this, sir, in order to calculate the fraction of the energy that is leaving surface 1 and reaching surface 2, sir.
Mm-hmm. Okay. Muzaffar, can you tell me something about Planck's law?
Planck's law. Sir, yes, sir. Sir, Planck's law, this law states that for a black body, sir, the spectral emissive power or hemispherical emissive power is a function of wavelength and temperature of the body, sir. Sir, expression for this, that is spectral emissive power is equal to the 2 pi c square by h upon lambda k power 5 e raised to power hc over lambda kt minus 1. So this actually tells us about that the spectral emissive power is the function of temperature as well as the wavelength of the radiation emitted by a body.
What is that spectral emissive power, Muzaffar?
Sir, spectral emissive power means the emissive power of a body at a particular wavelength, sir. It is also called a monochromatic emissive power, sir.
Okay. What do you mean by gray body, gray surface? What are gray surfaces?
Sir, gray surfaces, I think these are where there's this the spectral emissivity is not a function of wavelength, sir. So this means emissivity remains same for different types, the different wavelengths, sir. It is not a function of wavelength. That is, at thermal equilibrium, we can say that absorptivity is also not a function of this wavelength of radiation for a gray surface.
Therefore, what is Stanton number and what is the significance of Stanton number in heat transfer?
Yes, sir. Sir, Stanton number, sir, it is the ratio of this Nusselt number over Reynolds number into parental number. That's also called a Piclet number. Sir, it is used to, sir, Stanton number is used to relate it provides a relation between the second friction coefficient and the convective heat transfer coefficient, sir, in terms of Reynolds analogy, sir. That is Stanton number is equal to CFX by 2, where we relate the skin friction coefficient and the convective heat transfer coefficient, sir.
So for getting the more heat transfer, Stanton number is required to be higher or lower?
Sir, by increasing, yes, sir. Stanton number should be more for more convective heat transfers. It should have more values.
What is NTU of a heat exchanger, Muzaffar?
Sir, NTU is means number of transfer units. Sir, we use this approach to calculate the heat transfer in the heat exchanger when the information is not sufficient. That is, sir, all the temperatures are not given to us, so that we can't use the LMTD approach. Sir, we use this NTU approach to calculate the heat transfer. Sir, it is equal to the product of overall heat transfer coefficient in the area of a heat exchanger upon the minimum heat capacity, sir. Sir, if we keep this overall heat transfer coefficient constant and temperature difference, sir, it tells us about the area of the heat exchanger, sir.
Okay, Muzaffar, I think now I can provide you the feedback. Muzaffar, your delivery style, your confidence, your technical understanding is looking fine. You answered most of the question. I think you missed only one or maybe one question only, 1 or 2 questions, but remaining all questions you answered. You know, for a plain slab, the conduction resistance will remain same. It is not going to change. You know, what is total thermal resistance? Total thermal resistance is a summation of all resistances.
Yes.
So whether you are keeping the lower conductivity material inside or outside or in between, the total resistance will remain same. Okay, but suppose if you are having a cylinder, and a composite cylinder. And suppose you are having options of providing different material layers. In that
Yes,
case,
sir.
it is good to keep the better insulator inside.
Yes, sir.
Okay, as compared to the keeping it outside, because that is going to affect the total thermal resistance. So in case of cylinder, the total resistance is going to change. It is going
Yes,
to
sir.
depend on the order in which you are keeping different materials over the cylinder. But for
Yes,
plain
sir. In
slab,
this
the
case,
total thermal resistance will remain same.
yes,
Fine?
sir.
So remaining all questions, I feel you answered well. Like the some questions from radiation, I asked you. Conduction, convection.
Yes,
So some different questions I asked you from basic question mostly. Because in
yes, sir.
state level state level interview, they are going to ask you similar kind of basic questions only. Some practical questions also they can ask, maybe related to the heat transfer in transformer, heat transfer in radiator.
Yes, sir.
Okay, and how the
Yes, sir.
heat transfer takes place in a cooling tower. Okay, or
Yes, sir.
some basic common things also they can ask. But I feel you will be in a good position to answer, because your confidence, your knowledge is looking fine of this subject.
Thank you, sir. Sir, last time my answer was somewhat partially. Is it fine
No,
today
no, no.
also?
Very well,
I need.
very well executed, Muzaffar. Today, you
Thank you, sir.
presented very well. Your answers are looking very good, and in detail, sufficient detail, you highlighted the important things, Muzaffar.
Thank you, sir.
So this time,
Sir,
it was very good actually.
sir, last time I had one question that I said you on the WhatsApp as well. Sir, I was confused in this the critical point. Sir, the degree of freedom is 0, but when we calculate it by Gibbs phase rule, it comes out to be 1. So sir, it is creating a lot of confusion, sir. How
Actually,
is it so?
at critical point, we define the Gibbs phase rule like that: F plus P equal to C plus 1. Okay, so
Yes, sir.
you can use that relationship to find out the degree of freedom, or
Yes, sir.
the components will be different, or not component, the phases will be different. How many phases you are taking?
The 2.
You are taking 2 phases.
Yes, sir.
Mm-hmm.
Sir, actually, I was using for C plus 2. This means, sir, I had to use the modified Gibbs phase rule, C plus 1 here.
Yes,
Then
yes,
it is fine, sir.
yes.
It is fine, sir. Then
Yes.
it comes
Then
at 0,
then
sir.
yes. What is the reason behind
Yes, sir.
that? That I will discuss with you. I will get back to you through WhatsApp. So again,
Thank you, sir.
WhatsApp me.
Thank you so much.
When
Yes, sir.
again WhatsApp me. Okay, just say hello and mention your name. I will get back to you close to maybe 9:30 or 10 p.m. Fine.
Sure, sir. Thank you so much, sir.
Okay, Muzaffar.
Thank you, sir. Thank you, sir.